Good morning, good afternoon, and good evening. Welcome to day 4 of the Python Web Conference 2021. And to start off our PyData track today, I am actually going to be presenting along with Shane Hathaway, who's been a senior Python developer at 6 Feet Up. My colleague, somebody I've looked up to for years. I've known about Shane since I started using Plone in 2003. His name's been floating out there because he's been, as he'll tell you, responsible for a number of things that we all have to use in the Plone and Zope world. And so today, Shane is going to be taking us away with the presentation on Python and AutoML Vision.
So today, we wanted to talk about Python and a project we got to do with a client for machine learning. We used Google's AutoML to do automated document analysis. And here we go. So yeah, as Kim said, I'm a senior software engineer. I've been working with 6 Feet Up for just under a year. You can blame me for some parts of Zope and of Plone.
And particularly rel storage is the big thing that people in the Plone world use so heavily. And as you probably all know, I'm Kim Nguyen. I've been VP of Engineering at 6 Feet Up for about a year and a half, but I have been working with Calvin and Gabrielle and Carol and Chrissy for quite a bit longer in the Plone community and the Plone Foundation. I started off as a Plone developer. That's how I got hooked into Python. And at the university here in University of Wisconsin, Oshkosh, I was really happy to get involved in using Plone and using it for about 300 different websites, including intranets. But in particular, the reason why I'm really keen on machine learning projects is because a long time ago, I did a master's in computer vision and AI, but using old or classical techniques, not this newfangled machine learning neural network stuff. So it's really exciting to be able to use these tools.
Yep. And did you? Yep. Let's just go on. So the problem that the client came to us with was they have so many forms. They receive forms from many different companies and many different styles of forms. What you're seeing on the screen is representative of the diversity of forms. It's a different industry, but still there are just so many different kinds of forms that it took a small team, almost full-time work, just to identify the forms. And so they wanted help with creating a machine learning model and algorithm that would simplify all this for them, so they wouldn't have to run everything through humans. And here's one of the forms that you saw on the previous slide a little closer. These forms usually have a QR code, which you can see in the corner.
And the thing I forgot to mention is that this particular client is in the transportation industry and receives lots and lots of different forms, and they're not well scanned necessarily. There's a lot of varied lighting conditions, cropping, orientation, very challenging to take these paper forms and do something intelligent with them. And we are always pleased to talk about projects like this because these are real world problems that we can solve with machine learning and Python, because Python being the Swiss Army knife of machine learning and data handling, as we've seen in other presentations this week too.
Yeah, thank you. So our job was to just identify the forms, not necessarily read them. We didn't have to pull the form values out, just had to apply labels. And in this talk, we want to discuss what we identified as reliable technology, some less reliable technology, and what I like to call real work, things that aren't simple technological solutions. Now, it turned out in this project that we ended up with pretty much reliable technology. We shied away from less reliable technological decisions. And here were the requirements. We had to select a cloud platform. The client was already using Google Cloud Platform, so that was a pretty natural fit. And it turned out that Google Cloud Platform also has really good really good machine learning support. One of the things we had to do is, in a project like this, you would often construct a model and then let the client just use that model. But in this case, it needs to be ongoing training. They need to be able to submit new documents over time because their training set really does change over time. So we had to create something that would retrain automatically on its own. And we had to fetch the images using in the PDF form from Backblaze. And they required us to apply encryption to the maximum extent possible because the documents often contain personal information.
Right, and the reason why this particular client chose Backblaze was because it was affordable, and they liked the encryption model for storage. And the original target that the client had in trying to get in terms of accuracy of the decision model was about 60 to 70%. That's what they originally said would be a great success rate. But then we found over time that they actually changed their mind, and that number started to creep up to eventually 90% being their target. The other thing I'd say about these PDFs is each PDF represents a bundle of many, many scanned or photographed document pages. And so they just come in this big lump, this big bundle. As you'll find, we had original requirements and they changed a lot. And this is actually typical of the kinds of consultative engagements that we like to work with, because when you have senior developers, you can really engage in a prototyping and consultative way.
Yep. So we started using AutoML Vision because it is good for document identification, estimated to be less expensive, easy to use, and we found that it has a well-documented API.
And we'll be talking about the expenses later on too.
Yep. Other parts of Google Cloud Platform that we used includes Cloud Functions and Cloud Run. Now, it's interesting to see that Cloud Functions and Cloud Run really kind of cover this similar space. So we wanted to talk a little bit about the difference. Cloud Functions are really similar to AWS Lambda, and you simply put in some Python code or whatever language, and you can run it. Cloud Run, it has a similar execution model, but you build it from a Docker file. And so we needed Cloud Functions for most of the functionality, but we used Cloud Run for the image processing so that we could use the needed C and Java image processing libraries.
And here, it was particularly important for us to use serverless capabilities for the flexibility it gave us to spin up and spin down computing resources in essentially to limit costs as well.
Yep. Other parts of GCP that we used include cloud storage, which is a file system similar to S3. It was essential to use cloud storage because AutoML Vision requires us to store the images, at least temporarily, in cloud storage. It will not train any other way. We also used Firestore, which is a NoSQL-like database. We use that for tracking the state of training because we want to train as quickly as possible. So we farm out jobs, and each job writes to its own special key in Firestore, and then the code that's tracking the job can retrieve the state of the jobs very quickly using a simple query of Firestore. And we also used Cloud Scheduler, which is like cron, IAM for managing the access control. We wanted to make sure that only authorized people would be able to access this functionality. And of course, we use Terraform to manage the infrastructure.
And here we do want to say something particularly nice about Terraform, because that is the tool that we use for deploying systems like this, all sorts of complex applications in a repeatable way. It's the infrastructure as code methodology where you can essentially just recreate environments by repointing to a different set of servers. It's a very powerful tool that we like to use at 6 Feet Up.
Indeed. So the solution came out to essentially two parts, training and classification. Now, when we found that as we were discussing these things, they seemed really similar. So we'd like to spend a little time discussing the difference between what training is and what classification is. So when you train, the input to training is kind of like a Python dict. You specify a list of pages and the label that you want to apply to each page. In AutoML, you only get one label per page. And the output of training is a trained model. And then when you run classification, you also input a page, but this time you input the model, the trained model, and the output is a label.
And we'll be talking about some examples to illustrate more what kind of labels we were using.
Yep. So here's the training process. We wait for new training data. And when new training data arrives, we receive from the client the name of a PDF, which we have to fetch from Backblaze, an encryption key, and the page labels to apply to each page in that PDF. And then we wait for quiescence, which is also known as debouncing. The period that we wait has changed over the course of the engagement, but suffice to say that we wait a little while for new training to stop arriving. And then when we decide that it's time to run the training, we run 500 jobs concurrently, and we can do that easily using GCP. And they just happen to take about 10 minutes each. And in each job, we download the PDF, we extract the pages, and we read the QR codes. We try to read the QR codes from each of the pages. And we also prepare PNG images for AutoML. Once we have run all of those jobs, those fetch jobs, we create the AutoML model, and that takes hours. So we don't require any human to sit and wait for it because it could take a day. And then when that's finished, we deploy that model. We deploy it as a certain well-known name so that the classification can always run based on the latest model. And finally, when the model is fully deployed, we delete the temporary data and run back in a loop and wait again.
And here again, we have to go back to the original requirements. This particular project had very specific requirements about not having a fixed training data set for us to use. So in a standard, if you can call it a standard machine learning model deployment, you would train against a fixed set of data and then test against the other half of the training data. But in this case, the client was essentially developing and marking the training data as they went on. So their team of about 7 people who work with the documents, they would label the documents for specific types of documents and then provide that as training data. So that's why we had to set up this process to just periodically redo the training. And the 500 jobs that we set as a limit in this case was really to act as a balance between speed of training and cost control.
Mm-hmm. So the other half of the functionality is classification, and it's a bit simpler. We receive a PDF from the client and we extract the pages. And for each page, we convert to PNG and run that PNG through AutoML. And we reorient the pages. Sometimes the scan is turned. And the reorientation turned out to be a kind of fun thing to do, because the way it works is we run through Google's standard OCR engine, and the OCR returns a list of all of the words on the page and tells us what the orientation of each of the words is. Now, you would think you could just take any one of the words and say it's at this orientation and then reorient the page accordingly. But we discovered that there are a lot of forms that have rotated text, like say for office use only, whereas the rest of the text is oriented normally. So we had to make sure that we didn't accidentally reorient based on the for office use only text. So we had to take a sample of say 100 words out of the document and choose what the most likely orientation would be. And finally, we would read the QR codes and send all of those results to the client's webhook, because they didn't want to sit around waiting. This sometimes took a few minutes. So their webhook was always waiting for the results.
And that webhook allowed us to integrate into their existing system without disrupting or significantly altering the implementation of their production system. What I found particularly curious about this is, again, it's a real world problem where the scanning of the documents was not that reliable. And so the idea that we would have to figure out orientation was something that surprised us. The other thing too to note here is that even if a document was rotated correctly based on what we did, sometimes the document wasn't exactly 90 degrees off. And so even slight variations in the orientation, fortunately, were not a problem for AutoML for the way that we were trying to use it in this case, which is just to identify the document.
Yep. So Kim mentioned one of the surprises, and here are a few more. We discovered problems with DPI, dots per inch, QR code legibility, and label granularity, and we'll go over each of those. Dots per inch. Sometimes the resolution metadata from the phone scans is wrong. So for example, if you get a 300 DPI image, but the PDF claims that the image is only 72 DPI, then you could easily have an image with 10,000 pixels per side. And GCP limits the amount of RAM that we're allowed to use. So sometimes that would cause a memory overflow. We discovered that probably the best way to deal with that is just let it crash. And there was the separate process that still tracks the Cloud Run outputs, and it can simply tell Cloud Run to run the same pages again, but this time with lower resolution. And it's really kind of a rare thing. So we decided that it was best to leave it like that, and it serves as a test of crashing, make sure that our code can deal with crashes. And that was a kind of fun solution to that problem.
It's an illustration of the new paradigm of deciding that servers are dispensable and can be restarted at will, just with slightly different input conditions, as opposed to trying to go through a more convoluted process of identifying and verifying the resolution, comparing that to the metadata. That would be more CPU intensive and probably a slower solution.
Mm-hmm. Another surprise was the QR codes were not as legible as we expected. We went into the project with the expectation that if a phone can scan a QR code, then any of the QR code libraries should be able to scan it. What we discovered is the scans failed a lot more often than we expected, and we noticed that we could take an image of a document that we couldn't scan with a standard QR code library, and we would put it on the monitor, and then we would hold the phone, just about any phone, up to the monitor and scan it from there, and the phone would get it every time. Big surprise. And we had to, we took some time to understand why that was happening. And we decided that it was probably because we needed subpixel resolution. When you're using subpixel resolution, that means that you're identifying coordinates that are not integers. So instead of, say, x at 5 and y at 10, you want x equals 5.2 and y equals 10.3. So we searched for a library that was aware of this need for subpixel resolution. And we found one, BoofCV. It's able to identify subpixel corners and then run subpixel sampling. So here is a sample of the kinds of QR codes that BoofCV is able to scan. And you can see all sorts of terrible scans, and yet it can identify them. This is a sample of their test cases.
Yeah, it's surprising that phones just do this. And yet for our purposes, we have to go find an extra library, given the capabilities that you'd assume to be in things like AutoML. This particular library worked very nicely. Those are really interesting conditions that it can handle.
Yeah. All right. The final surprise that we want to talk about was managing the label granularity. So here's some pictures, some public domain pictures of 1967 Ford Mustangs. Now, let's say that you are creating a machine learning model, and you're trying to identify these Ford Mustangs, these beautiful cars. And you're just kind of running on autopilot, and you accidentally tell it that you want to identify 67 Ford Mustang Cobras. Now, can you really identify from these pictures which one is a 67 Cobra? The truth is you can't, because Cobra is just the type of engine. And there were often some markings on the outside that identified the Cobras. For example, on the left, you can see that stripe on the near the fender. that sometimes says whether it's a cobra, but it's really not a reliable indicator. So if you were to try to train based on that label, it's too granular, and you're just going to confuse the model. It's going to try as hard as it can, but its confidence level will be very low.
I like how when Shane and I were working on this slide, he referred to it, well, if you're a car person, you'll just know that this is the case. And I don't know, I consider myself to be a car person, yet I didn't know this.
Yeah. All right. So through this project, we sort of identified what I would call the real work. The two main things would be balancing the label granularity. That's probably a common issue when you're doing a machine learning project. We feel like we did achieve a good balance, but the solution was very specific to the client. It's something that you have to work on. That's going to be a really specific solution. Let's see. We had to work pretty hard with the client to achieve the necessary training quantity and quality. We discovered that it really wasn't sufficient to have any less than about 1,000 of each form that they want to train on, 1,000 samples. So we imagine that achieving that quantity is a pretty common issue for projects like this. And we discovered that there's really not very much room for error. The client sometimes gave us samples with incorrect labels, and that really confused the AutoML model very quickly. And I still wonder whether that's really a common issue. It seems a little crazy to assume that the training model can handle quality issues in the training, but I don't know, maybe that is a common thing.
Trying to find that balance was an iterative process of training and then looking at the accuracy of the model that came out of it and having to go back and adjust multiple times.
Yep. Fortunately, Google does provide metrics that help you understand how good your quantity and quality really is. We'd like to go over some of the good choices that we made. And the first good choice, definitely Python. Let us iterate very quickly. The requirements changed over time. Python just didn't break when we mixed Python, C, and Java image processing libraries. Another good choice was AutoML offers the choice to, after you build a model, you can expand that model. We decided not to use that. We decided to rebuild the model from a new training set every time because it just seemed simpler that way. And that allowed us to iterate on the label granularity. So for example, we might start with a label of a 1967 Ford Mustang for a certain image, but later we can automatically decide that really that we should be training on 67 Ford, or in some cases, the more granular choice was better, the 67 Ford Mustang Cobra, depending on the label.
And because of the way that we set up the retraining of the data and the acceptance of new training data from the client, we were able to just recreate those training data sets for rebuilding the model. We didn't have to just keep adding. We maintained control over the original training data.
Terraform was definitely a good choice. It made the transition from development to production pretty easy. It would be nice to be able to share some Terraform code, but I have to say that Terraform is sort of an acquired taste. It it's easy to understand once you're familiar with it, but it doesn't look so great when you're not.
But it's really useful. It's a really useful tool for being able to recreate development and staging and production environments like this. It's a tool that just gives us the flexibility to recreate environments at will.
And the final good choice that I wanted to talk about is serverless. It definitely liberated the serverless design liberated us from most admin and DevOps duties. The cost is minimal when we're not running training. And it's very easy when you have a large requirement like 500 concurrent machines. You can just do it.
And again, cost was a really important issue for a client. And so this was really the way for us to go. The ability for us to avoid having to manage servers and to watch the performance of servers was just something that we were freed from having to do. In the AWS space, I know that running Lambdas is really inexpensive for the first several million calls. So serverless is definitely a tool that you should consider using in your deployments.
Now, this talk wouldn't really be complete without us discussing some of the things that some of the choices that we could have made that would have been better. We should have watched the AutoML costs a little better. We should have learned a little more about encrypting images ahead of time. And it would have been helpful to know that this was a workflow-like process. So we'll go over each of those. So for a month, the AutoML costs were rather high. They were over $8,000, and they dwarfed anything else in the GCP costs. And we learned from that month that we should have been monitoring that. And we discovered that only about 2,000 samples were needed for each label. They had some forms where we had over 10,000 samples, and just no need for that. The number of samples affects the training time. We also learned that it wasn't really productive to train every day. We could run training every 2 weeks or so, and that was enough. And so once we optimized those two things and a few other small things, the total cost for the client at GCP was only about $100 a month. So it became much more reasonable.
Right. And so you could say, is $8,000 a month unreasonable? That's going to depend on the client, obviously. But seeing how much we could get the cost down to, it's clear that the savings are there if you're paying attention and you choose to optimize.
Another thing we learned is, although they had the encryption requirement, we learned that AutoML requires images to be stored natively in cloud storage during training. There was no way to convince it to decrypt on the fly. So because training can take a day or more, we were concerned about that because, you know, the images were unencrypted for a full day. But the truth is, cloud storage encrypts everything at rest anyway. So we weren't completely disabling encryption. We just we learned that we couldn't use the client's specific encryption algorithm. And again, the project might have been simpler and quicker if we had known this limitation ahead of time.
And it's always interesting to see comparisons between the different cloud service providers. For example, I've learned this week at the conference, at one of the earlier talks, that AWS has a new feature, a new function called S3 Object Lambdas that would let you invoke code as you're reading from an S3 bucket and transform that code and maybe filter it out so that a function like that, had it been available in Google Cloud, would have allowed us to do that kind of decryption while reading from cloud storage.
And finally, the project turned out essentially workflow-like. And what we mean by workflow-like is that training is a series of steps that need to be monitored. We need to make sure that each process completes and before going on to the next one. And we need a faithful record of each process that runs. And it would be really useful to have sort of a UI for that. So people can go in there and just rerun a step because it broke because, I don't know, the cloud was having troubles that day. So it would have been useful to use a tool like Cloud Composer, which is a hosted version of Apache Airflow next time. So the bottom line, there are about 11 very successful labels so far. The AutoML model claims to be about 99%, actually greater than 99% accurate for those labels. And there are over 1,000 samples for each of those labels. Unfortunately, the client needs a lot more labels, but fortunately, it's an ongoing training process. Over time, they should be able to achieve a lot more successful labels. The ongoing costs appear, again, to be about $100 a month, but that will increase a little bit with the size of the training set.
What's interesting to note is the greater than 99% accuracy is wonderful, but because occasionally the model does make a mistake, it would be really helpful for there to be, this is where explainability would have been important for us to be able to see, for example, which parts of the image were relevant to the incorrect decision so we could better tune the way that the model functions.
Yep. All right. This is an XKCD comic that was published in 2014, and I feel like it's really relevant. So there's a manager and a developer, and the manager says when a user takes a photo, the app should check whether they're in a national park, and the developer responds, "Sure, that's easy. Just use GIS. Give me a few hours." And then the manager adds, "And check whether the photo is of a bird." And then the developer responds, "I'll need a research team in 5 years." It's often difficult to express to people why some things are much harder than others. But this was published in 2014, and it's actually no longer accurate because machine learning is now available to the masses. It's democratized. So this is simply not true anymore. And we're really excited to see what's coming. There is a lot more machine learning becoming available.
It really is amazing how far neural nets have come from being toys.
Yeah. All right. So it was a pleasure to be able to give this talk. Excited to be working in the machine learning space and Python. It's a very productive way to do it.
And we're always interested to hear about your machine learning projects and to find out if there's a way we can help you. Thank you very much, Shane.